Okay, everybody, here we go. All right, so this is the example off of the last 5-2. I just snipped it. If we can use this, I guess the whole thing is, when you look at that integration there, I don't think you have a clue what to do. Okay, it wouldn't be a basic one. So this is one that you'd have to say, okay, what does this look like graphed? This graph, who knows what that looks like?
The parabola to the side. I mean, no, that's the.
Okay, do you know what this looks like? It's a circle with radius 2. Okay. Do you know what this is? The same thing, right? So then this is that, which is half of a circle. Okay? So this is half of a circle. It looks like the top half or the bottom half, because this would be the circle x squared plus y squared equals 4. This is at 2. Okay? You think that's the top half or the bottom half? The top. That's correct. So this piece right here is radical 4 minus x squared. Okay. So do we know how to find the area? Because that's what an integration is, right? Reed and Mary Grace, are you having issues? Okay. All right. Do we know how to find the area of the circle? What is it? R squared. So if we can find the area of the circle, we can find the area of half the circle, right? Okay. Look, from -2 to 2, here we go. So we're talking about this circle right here. So half of pi, what did we say R was? 2. Okay. Simplify, you get your integration. Okay, 1/2 pi times 4 or 2 pi. Okay. Now there is not a method other than that method and plug it in the calculator method that's going to give you the answer. Yes, your calculator will give it to you too. So, but you're going to have some of those that you're like, I don't know how to do that. Don't forget about -2 to 2, the geometry behind the integration, because the geometry is, if it's a perfect, geometric shape that you already have a formula for, then you can totally do it that way. Should be 6.28, blah, 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 when it comes out, right? There it is. Okay? So, anyway, just FYI. Don't forget about the geometry, shape, if you get stuck. Because we don't get into integration as much as we did derivatives. So, there are going to be things that you're like, wait, I don't remember how to do that. I don't know how to do that. And then that would be an option to think about the geometry. Okay? All right, so 5-4, we're going to split up. Okay, we're going to look at this. It's kind of a weird concept at the beginning. It shows up a fair amount of times. Okay, so we're looking at g of x being a function of the integration. Okay, so it's kind of a weird thing. Don't try to, like embrace it all at once. But check this out. G of x, black pen, equals this integration. Here's x again. So g of 1 is going to be the integration from 0 to 1 of f of t. What happened to my f of t? Is there anything drawn on there for you? Oh, wow. Okay, there's supposed to be something on here. Let's just draw g f of t here. Let's just say it looks like this. This is f of t. I'm not sure what happened to it. Okay, or y. Okay, there's t. Okay, so g of x is the integration. All right, let's put some numbers in here. They've disappeared too, so we're going to go from 1 to 2 to 6. That is bizarre. All right, so let's say this is 1, 2, 3, 4, 5, 6. Okay? I'm not sure why I'm putting those vertical lines in there. All right. All right, so G of 1, how would we illustrate that? G of 1, if it says it's the integration from 0 to 1 of f of t dt, what would it look like? On the graph, you shade in 0 to 1, what do you mean? The vertical line from 0 to 1. This is, yes. That is G of 1. Okay? So they're going to do that, and then of course there's going to be applications. But okay, what does G of 2 look like? Again, if we're using this formula, and this just says that G of x is the integration of f of t. So we're going to go from 0 to 2 of f of t. Okay, so I'm going to shade that from 0 to 2. So that's all this piece. This is, the red is G of 2. Okay? And then the G of 6 is going to be in blue. And the G of 6 is going to be from here to here, all of this. Okay? Because that is the integration from 0 to 6 of f of t dt. Okay? So, a function value, and it, again, remember G of x, G of 6 is a number. Well, what number is that? We don't know, but we do know it's the number that represents this area under this curve from 0 to 6. Okay? All right, let's take a look at another. Does anybody have any questions? I know it's like, where's this going? That's what we're doing. We're going somewhere here. Okay, G of x equals the derivative of from 1 to x of t squared d squared. Okay, we're supposed to evaluate that. Okay, so how do we do that? How do we evaluate an integral? Antiderivative, good advantage. All right, what's the antiderivative? 2 to the 3 over 3, okay. 1 to x. All right, the x is not going to go anywhere. Just going to change places, okay, because it's not a number. All right, so what's that? X cubed over 3 minus 1/3. Okay, so that's the value of G of x. All right, it's G of x, just a reminder. Now, that's G of x. What's G prime of x? What is it? Here's G of x. What is it? X squared. Okay? I heard t squared. So you're already picking up what I'm trying to illustrate here. Anybody want to put that in words, what we just did?
Basically, you're finding your original function, and then you realize that, like, what you found is what you started with, because it's the derivative.
Because the derivative and the antiderivative are like opposite functions, right? Okay. So if I know that, and all I really need, G of x, if G of x is this, and all I really need is G prime of x, can I just put in this in here and be done with it? Okay. But again, it's that whole, okay, wait. I just went in a big circle and just ended up swapping out my variables, right? That's all I did. Okay. This is going to be the easiest thing you'll do all year, and it's going to be the first thing you forget because it's so easy you don't have to think about it. Okay? But this is like big circle, G prime of x should be just, I'm going to put this in for this, and I'm done. because we know the next slide is the derivative of the antiderivative is the original function, basically, which is what Madeline was saying. Okay, fundamental theorem of calculus. Okay, certainly the most important theorem in calculus. I know the other one claimed to be very important, but it really wasn't, the MVT, remember? Okay, because it tells you there's a connection between the two branches of calculus, the differential, finding the derivative, and the integration, which is definitely connected. They're opposites of each other, right? Okay, so we're going to have two parts. Fundamental theorem, part 1 says f is continuous on the closed interval AB. That seems to be what all of our theorems so far, EBT, MBT, they've all started out like that. Okay, then the function big F of x is the antiderivative, and if it has a derivative at every point in there, okay, that sounds like f is differentiable on the open interval, which again is another common theme for our theorems. And the derivative of big F is the derivative of the integral. That's what this says. Okay, we're taking the derivative basically both sides. Derivative of this side looks like this. Derivative of an interval look like this. And basically all you do is take that variable and put it in there. Okay, don't get hung up on words. It basically says that every continuous function has an antiderivative, and the process of differentiation and integration are inverses of each other. Basically says if you take a derivative of an integrable function, then you're back to that original function, okay? Which is very hard to say, that's why I don't get worried. But we are going to do this a lot more than you think. Okay? Integration, remember, is a number. So basically, we're going to turn integration into a function with this a little bit. And hopefully it won't continue. I know it's kind of confusing when you just talk about it, but let's show you how you do it. Okay, so derivative of cosine integration with respect to x. This x and this x need to match. Okay, now in the homework that I gave you, this last homework, page 373. Okay, here's what the directions say. Find the derivative, blah, 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 and then number 7, maybe it will be something like this. Whatever. Sorry, that's mumbling. Okay, so the directions are up here. You have to say, all right, don't do this. Sorry. Right? Because that's simply not true. This would equal, this would equal that. Okay? So what I'm telling you is do something on your homework to indicate that you know you are taking the derivative, and that's why the integral stage thing is going to drop off. Okay? All right, so basically, we're going to take the derivative of this integration. We have pi down here. Okay, let's just remind ourselves when we went over here, did this ever come into, like, is that even going to matter, ever? No, because it's going to be a constant if we took the antiderivative of it, and it's just going to, it doesn't matter. So bottom line is, this just needs to be any constant. Okay? At bottom lower limit of your integral. Okay? That's what it needs to be. So far, so good on these problems, okay? Now, if we did this, typically we would just do the antiderivative and then come back and do the derivative. We should be back to this, except what will be our variable now, x, okay? And we don't need a plus c, none of that, okay? That's all there is to it. The derivative of the integral from pi to x of cosine t dx dt is cosine of x. Okay, this needs to be a single variable. Okay, like this is a single variable. Okay. However, we're going to run into a problem with that one because that's x squared. That's what I mean by it, not single. Even if it was 2x, it's not a single variable. Okay? Again, this x and this x should match because otherwise it's same with this and this match. Okay. Tell me what the derivative of the integral of 0 to x of 1 over t, 1 plus t squared dt equals. 1 over what? 1 plus x squared, done. Very simple. Okay. Now, again, if you look, that's inverse tangent, right? The antiderivative is inverse tangent. And then when you take the derivative of inverse tangent, there you go. So you don't have to go there if you remember. Just put the x in place of the variable. All right. So you want your upper limit to be a single variable. This is what we're talking about here. Okay? The lower limit has to be any number, doesn't matter what the number is. Okay. So when we have that, we're going to have to remember the old chain rule. Okay, we're going to have to take the derivative of it if it's not a single. So we'll say not single here variable. So we're going to slip this in here just like we would have. So now we have cosine x squared. Since we're using the chain rule, we're going to take the derivative of x squared. That's the inside function. Okay, that's what the chain rule is. Take the derivative of the outside with the composite and then take times. So what does that really equal? 2x cosine of x squared, done. Okay, so you slip that in, and then if it's not a single variable, then you have to take the derivative of it. Okay, all right. This one is different again. Okay. The lower limit is supposed to be the number. Our upper limit is the number. Our function is supposed to be at the top. Our lower limit is the bottom. So, any suggestions about what we could do to fix that little problem? Negate it. Good job. So I'm going to take the derivative of the negative integration of sine of x. No, I'm not. 3 sine of x. That one of those properties. Is that t squared? dt. Okay? And you can switch the upper and the lower limit if you negate the integration. Just going backwards. Okay. So now we can treat it just like we did this one. We've got our number here. Constant is good. But again, we're going to have to use the chain rule to take this down to, okay, so here we go. Who wants to do it? My negative's just going to hang around. What's the derivative of the integral from 3 to sine x of t squared dt? Go ahead and try it. Negative just going to hang around. Got it? What do you got, Jessica?
Cosine x minus
Did you lose your negative, or I don't know? I didn't do it. So you said cosine x.
negative cosine x sine x squared.
Do you mean sine x squared, or do you mean sine squared x? Do you mean sine of x squared, which is what you said?
Yeah.
Or do you mean sine squared of x, or do you mean sine of x squared like that? What's that? Which one does she mean? Well, either of the second or the third. The second is the same as the third, okay? But when you're not squaring the x, you're squaring the t. So this goes into here, right? All right, so then that becomes, I'm just going to write it here, sine x squared, okay? And then where this cosine x comes from? Derivative, because sine of x is not a single variable. There's a chain rule application there. So, okay, and the derivative of sine is cosine, right? Not negative cosine. The cos have the negative derivatives, right? Okay, so this would be cleaned up, nice. Get my right pen out here. Sine squared of x. That's the most efficient way to write it. I like how you put the cosine, negative cosine out front, Jessica, because that's more simplified. This is not what we want, and this is really not how we write it. So this is best, okay? Now, if you are putting this in the calculator, however, for some reason, if you're doing integration, this is how you have to put it in the calculator, because this doesn't work. When you put your sign in, and you all know that already, right? When you put your sign, the calculator gives you you can't square it back now. Okay, so in order to square sine, you have to do parentheses sine of x squared, the old-fashioned way. Oops, not that one either. I got to put another parenthesis in. That's how you, and I got something there for sine of x. So that's why it gave me a value, but, okay? That's how you have to put it in there. I almost said different word, didn't I? Yeah. All right, so that's, again, very easy, but it's like, does it make sense? Okay, and that's why I did one by hand, a real easy one, just so you could see, like, why am I doing that when I can just do that? Okay? And here's another piece of the thing. I know I got another couple examples. Sometimes it's something that you couldn't find the derivative of. You couldn't find the integration of. So if you kind of want to do it, I'm just going to do it the long way because it really makes more sense to me. Well, sometimes you couldn't do that integration because we're very limited in what integration we can do right at the moment. Okay. So one last one, I think, and then we'll quit for the day. We'll save part 2 for when we all are here. Take the derivative with respect to x, which is what the ddx is, of the integral from tangent x to x squared of 1 over 2 plus t to the 4th radical. Okay, so first, what do you notice about the upper limit and the lower limit? What? They're both functions as opposed to what we know to do. So here's what we're going to have to do. We're going to have to split it up. Okay? We're going to split this up. So I'm just going to go ahead and do ddx. Okay. Let's do tangent of x to 0. Okay. Plus 0 to x squared. Hold on. Okay. Now, the only thing that you get to question right now is, first of all, I'm going to question you. Is that integral the same as the integral that we started with? Now, you don't like 0? Mary Grace?
I don't know, I just hard to get it.
It doesn't matter.
But how do you have a 0 in between?
It doesn't matter. Because it's a non-issue. When we do the derivative now, remember the derivatives of the sum is going to be the sum of the derivatives. And I'm not trying to be snarky. And I love that you're thinking about, wait, is that...
I was used to the negative.
Okay, hold up. You're already getting ahead of me. Come on. I can't even write that fast. I'm just teasing. Okay, I love that you're ahead of me. Okay, so, correct? The derivative of the sum is the sum of the derivatives, right? All right, now, tell me what you want to do with the whole, this one's totally doable, right? Okay, this one's a problem because the upper and the limits are switched, so we're going to do that whole, what? Negative thing again. Okay, so negative integral 0 to tangent of x. I don't know why I'm rewriting this again, because I really could be doing it instead, but just be very clear. Okay? So I negated, so I can switch my limits around here. Righty? Now we should be ready to go. Now you see why it doesn't really matter what number I would use. I could have used pi. I could have used e. I could have used 12,000. Just throw some number in there. It doesn't matter because it's moot. Okay. So what's the derivative of the first integral? What's the derivative of the first integral? What's going to happen? This is going in here. All right. So what does that give us? Negative 1 over 2 plus tangent to the 4th x. Anything else? Secant squared. Because that, remember, is, let me just do this step by step. And that's the tangent derivative. Okay, clean that up. I'm just going to throw this negative up here with the secant squared, and then 2 plus tangent to the 4th x. Okay? All right. What's the second derivative? All right. Give me a minute to do it. Go ahead, Megan. What you got?
1 over 2 plus x to the 8th times,
Wait, is that a radical?
yeah.
Okay.
Times the derivative of x squared,
And you were doing this.
Yeah.
Okay. All right.
which is then like 2x over.
And derivative of x squared? Okay. So then this one becomes 2x. Okay. That's pretty, isn't it? Is there anything we can combine there? I mean, it could be, but it would just sort of look like this on the bottom eventually. So I really doubt that that's going to be any better looking than what we got right now. So here we go. There's your answer. Okay. That would be the denominator if you wanted to get a common denominator. But it may be a, one of those multiple choices that you're like, oh, okay, I guess I could put that together, but it's not really necessary. Okay, any questions? All right. So I know it looks like